In this video, I want to talk about the timing of combinational logic circuits. So up until now, we assume that whenever we change the input to a logic gate, the change at the output happens instantaneously. So we didn't consider any delay between the time that we change the input and the time that that change in the input is reflected at the output. So conceptually, this is a valid assumption, but when you are trying to build a digital logic circuit, this is not valid anymore because we have delays between a change in the input and change in the output. And the answer to this question can help us in building faster circuits, or to put it another way, how fast our circuits can be. So basically, if I want to show it in a simple timing graph, we have this generic buffer here. We have A as the input and Y as the output. So the previous assumption that we had was if A is 0 now and then becomes 1 at exactly the same moment, so I call this T1 time 1 here, the value for Y also changes from 0 to 1. One thing that happens is that the change from 0 to 1 does not happen instantly itself. There is a very short period of time. So in reality, the change is shown like this. So not at a vertical line, but as a line with a slope. Of course, in grand scheme of things, this slope can be very, very small. So we can assume it to be 0. But for the purpose of this example, we assume that this time is not 0 either. And now let's say we assume the time at which the input changes. We put it at the middle point here between these 2 points. Because any physical object or component can have some delays, the change that we apply to the input would take some time to be reflected at the output of this generic buffer. As you know, time always moves forward, right? So let's just go over a couple of definitions that are very important in the timing analysis of combinational logic circuits. So the first definition that we have is what is called the propagation delay. We show it with T subscript PD. PD stands for propagation delay, and it is equal to the maximum delay from the input to the output. So let's say if we have a logic gate, we can say the propagation delay of this gate is 20 nanoseconds. That means that at maximum it takes 20 nanoseconds for a change in the input to be reflected at the output. So that is the definition of the propagation delay. The next definition is the definition of a contamination delay. We show it with T subscript CD. CD stands for contamination delay. And that is the minimum delay from input to output. Basically, that is the minimum delay that it takes for that specific gate for a change in the input to be reflected at the output. So graphically, we can show it like this. We have A as the input. As you can see, A is either 1 or 0, right? when we show it like this, that means it can be either 0 or 1, depending on the situation. It goes from 1 to 0 or from 0 to 1, but the point that we care about is this middle point, that we just say this is the point of change. So from the point of change of the input, the maximum time that it takes for the change to be reflected at the output, I show it with this blue line, is what is called the propagation delay, T of PD. The minimum time it takes for the change to be reflected at the output, we call it TCD. It's from the point of change, and this point here is shown with gray color here. So you might ask, why do we have two values, two amounts of delay? Why do we have both a contamination delay and a propagation delay? In another word, why do we have basically a range, right? Why is not the delay fixed? So delays are usually caused by capacitance and resistance that we have in the circuit. It also happens as the result of the limit in the speed of light. You probably have never thought that the speed of light, as fast as it is, can be still limiting for us. But just keep in mind, we are working with electrons, right? Electrons move fast. So for this case, for the timing of logic circuits, the speed of light is a limit. If the speed of light was infinite, which basically means that the speed of moving electrons could be infinite, then we wouldn't have this issue with the delays. The answer to the question why we have different propagation delay and contamination delay, or more specifically why we have a range of delays, not necessarily one single delay. There are a few reasons. The first one is that we may have different rising or falling delays. So if I go back, it is possible that the delay between the input going from 0 to 1 or going from 1 to 0 be different for different gates. For one, you are changing a voltage from 0 volt to let's say 5 volts, right? That is, physically speaking, that is a different process that a change from 5 volt to 0 volt has, right? So because of that, we may have different rising or falling delays. The other reason is that we may have multiple inputs for our logic gate or our logic circuit, and some may be faster than others, right? So that's another reason that we may have different propagation and contamination delays. Another reason is circuits can slow down or speed up when they are either hot or cold, right? This is something that you may have experienced for yourself too. So because of all these reasons, we basically have a range of values for the delays for each individual logic gate. So now that we know this, let's just go over two extra definitions that are very important in timing of combinational logic circuits. The first one is the definition of the critical or the long path, and the second one is the definition of the short path. So let's just take a quick look at this function here. This logic function has 4 inputs. We have A, B, C, D as the inputs and one single output. If we go one by one, we have A and B ANDed to create this internal node and 1. So this is AB. Then the result of the first gate goes through this OR gate with input C. So N2 equals AB or C. Finally, what we have is that the result of this OR gate or N2 goes through this 2-input AND gate with D. So that makes the final output to be AB or C ANDed with D. So this is the function that we have for Y. So as you can see here, input A to reach the output has to go through 3 separate gates. The same is true for input B too. On the other hand, for input C, it only needs to go through 2 gates. The path for D is even shorter. From D to the output, you only need to go through 1 gate, right? So now, based on this, and assuming that the delays, basically the range of the delays for all these gates are exactly similar, you can define the critical path as the longest path from any input to the output. So we have TPD, the propagation delay of the whole circuit, as 2 TPD of AND gates. So we have A or B that go through 3 different gates. 2 of them are AND gates. 1 is an OR gate, right? So we have 2 propagation delay of AND gates because we have 2 AND gates in the path of A or B, plus a propagation delay of the OR gate. For the shortest path, we consider the path with fewer number of gates, and we sum up all the contamination delays in that path. So here, since the shortest path goes from D to Y and it only goes through 1 gate, the contamination delay of the whole circuit is the contamination delay of this single AND gate. So this is how we define the critical path or the short path in any logic circuit. However, it is possible that you have some additional elements too. So let's just say if you had this extra element here, right? In this case, you had D going through this inverter and then this AND gate, and C had to go through this OR gate and this AND gate, right? So between the two, which one is the shortest path? In that case, you need to see what is the contamination delay of this inverter. So if the contamination delay of this inverter is larger than the contamination delay of this OR gate, right? And in that case, the shortest path could be from C to Y, right? So this is something that depends on the specific example, but generally speaking, if you know all the propagation delays and contamination delays of the gate, you can easily calculate the critical path and the shortest path of any logic circuit. So you might ask why these definitions are important. One of the reasons is because of the glitches. So even though we design our circuits in such a way to behave in a specific manner, right? It is possible that because of these additional delays that we don't account for when we come up with the Boolean equations, we create some unwanted states for the outputs of our circuit. So glitches happen when a single input change can cause multiple output changes. So let's just take a look at one example here. So here, as you can see, we have A, B, C as the input, and we have Y as the output. So if I want to come up with the function that describes this Boolean equation, I notice that A goes through this inverter, so that means that this is A bar now. B goes through this inverter. Here we have B bar. A bar and B bar go through this AND gate, so the output is A bar, B bar. On the other hand, we have B here and C here going through this AND gate, so we have BC here, and then these two terms are ORed together, so Y is A bar, B bar plus BC. If I create the Carnot map for this function using A, B, and C as variables, basically I transform these terms into equivalent ones or zeros in the Carnot map. This is the Carnot map that we have here. So we have a 2 to 4 Carnot map. I used A and B to represent the columns. I used the gray code again, and I use C to represent the rows. We have 1, 1 here, 0, 1, 0, 0, and then finally 0, 1 here. So if I follow all the steps of the Carnot map, create circles of size power of 2 as large as possible, so I can create these two circles and then write the function again. So this function is exactly the same as this one that I have on top, right? So now the question is, what happens when A is 0, C is 1, and B false, right? So A is 0, so here, when A is 0, C is 1, and B false. B goes from 1 to 0. So what happens when I go from this place in the Carnot map to this one? What happens? So let's just create a timing diagram and see what happens. So at the beginning, A is 0, B is 1, and C is 1. So let's just call this time 1. So when this is the case, the output here is 1 because A is 0. The output here is 0 because B is 1. Here B is 1 because we have B itself, and here C is also 1. The output of this gate is AND the AND of 1 and 0, which makes the output 0. So this is what happens in time 1. For this second gate, we have 1 ANDed with 1, so the output is 1 at time 1. So now we have 0 and 1 ORed together, which makes the output at time 1 to be 1. So this is what happens at the first stage of the Boolean function, at the beginning of the running of this Boolean function. So now what happens is that we have A and C to be fixed at their own values, but B changes from 1 to 0. So here we have B going from 1 to 0. So this one happens instantly because there is no gate in this path, right? So at time 2, you might say, we go for B from 1 to 0. So this happens instantly because there is no delay here. For this one, we have the change, but this happens at time 2 plus a certain amount of delay, right? So this doesn't happen instantly. So let's just say what happens in this very short amount of delay. So during this time, during this delay, this value is still at 0, which makes the value for N1 to be again 0. While for this one, since change from 1 to 0 happens instantly, the output of this AND gate becomes 0 sooner than this one changing from 0 to 1. So in the short amount of delay that we have here, these two, so this is time 2, you can say, and this one is at time 2 plus delay. So in the short delay that we have, both of these are at 0, which makes the output Y to become 0. And finally, after the delay is passed, we have 1 here and we have 0 here, which makes the OR to be 1. So this is what's happening after time 2 plus some delay that is introduced as a result of this inverter. I should note that I assume that the delay between these gates are all exactly similar, right? So if the delays are completely different too, then you may have larger or smaller delays, right? But if I assume the delay, the amount of delay that each gate is introducing is exactly the same as the other ones, just because this path has to go through this extra inverter, this extra amount of delay, which cause for the output to have this unwanted change. So let's just take a look at the timing diagram and see what happens here. So as I said, A is fixed at 0, C is fixed at 1, so we don't change those. So that means that the circuit is settled down at A being 0, B being 1, and C being 1. So we only have one change, which is B going from 1 to 0. So here, B goes from 1 to 0. The change for N2, which has one less gate than the N1 path, happens sooner than the change in N1. Because again, it has fewer gates in its path. So because this change happens sooner, that causes the output to change even before the change in N1 is completely settled, right? So because of this fact, as you can see, we end up with this unwanted case. Because if you consider the inputs as they are, so A, B, and C being 1, for this the output is 1, for A being 0, B being 0, and C being 1, again the output here should be 1, right? But just because we have a delay for input B, we have this unwanted value for the output. So this is as a result of the delay that we have. So this is what we call it a glitch. We only change one input one time, but the output changed twice. So this is how building combinational logic circuit can be different than having all the assumptions as perfect as possible, which basically assuming that there is no delay. So now the question becomes, how can we fix these glitches? One way to fix a glitch is to make sure that we have overlap between the circles that we use to represent the function with in the Karnaugh map. So initially we only had this circle and this one, right? As you can see, this circle is completely separate than this one. There is no overlap between them. Just by simply creating this extra circle that doesn't add to the functionality of the function in any way, because all the ones were included in the circles before, right? So there was no one in the Karnaugh map that wasn't accounted for. But just by adding this extra circle that can account for the overlap, we can avoid the glitch that we have experienced before. So I highly suggest you go through the timing of this new circuit and see if you still encounter the same glitch or not. Of course, as you can see, this was a very basic example. So when you have circuits that are more and more complex, it is very hard to account for all the possible glitches that you may have. So there are other ways to avoid these glitches. So in reality, what happens is that we use a technique which is called synchronous design, which basically help us to avoid these glitches. It is very important to recognize a glitch, and this is usually done in simulations or using an oscilloscope, which is basically a device that you use to visualize waveforms, because it is very hard to build a circuit and actually create it and then try to look for the glitches. So while you are in simulation, it is much easier and cost effective to try to recognize a glitch. Also, it is not possible to get rid of all the glitches, because for this simple example that we had here, we only change one of the inputs. What if we are working with a very complex circuit that many of the inputs simultaneously transition from one value to another, right? So these also can cause glitches. So if I, for example, want to emphasize this, let's just say if we want to go from this cell to this one. So as you can see, going from this cell, this is basically equivalent to a 1, 1, 1, right? A, B, and C are all ones, while this one is 0, 0, 0. All of them are 0. So as you can see, going from this to this, all of the inputs are changing. Do we have any glitch? You can easily verify it using the previous implementation, right? But the answer to that is you probably have a glitch, right? Even if it's not in this circle, in a very simple circuit, slightly different, you may end up having a glitch going from this cell to this one, right? So at the end of the day, you cannot get rid of all the glitches, but there are some that you can use some techniques either by creating extra overlaps or extra paths for the input to be delivered to the output, or by using the concept of synchronous design to get rid of the glitches or overcome them. You will see later on how we do synchronous design, more specifically when we work with sequential logic circuits. So in this video, we saw how we can use and define different terms and different delays of combinational logic circuits. We saw contamination delays, propagation delays. We saw that how we can use these definitions to recognize the critical or the longest path in a circuit or the shortest path in a circuit. And also we saw a few examples of glitches that we may encounter in a combinational logic circuit